We're going to change platforms here. I have a program that is so old, it will not run on modern operating systems that are 64-bit. So I have to bring in my old laptop. This program is called EM Fields. It was written by David Trowbridge, a friend of mine. Dave and I used to share an office in Lillian's research group. He went off to become he was in charge of all the physics animations in Microsoft's CARTA program. And so he went to work for Bill Gates. And he tried to recruit me. He invited me over and tried to get me to join his team. I went over there. It's amazing. There's food everywhere. Everyone was at Levi's. It was relaxed. But I said, no, Dave, I got to teach. I have to be a teacher. So years later, I was talking to Dave, and I said, so how's your job going? I said, I had to retire years ago. My stock options just went through the roof. I said, well, what do you do? I said, I just go around to elementary schools and do physics demos with them. Oh man, that's such a cool job. So I chose wrong. So this program of David's allows you to put sources. I'm going to put a -4 next to a +5. Now, this might be a +5 coulombs and a -4 coulombs, or a +5 microcoulombs and a -4 microcoulombs. It's all relative. Now, his program allows you to click anywhere, and it will give you the electric field vector. That's the field, the middle thing, the E, okay? And when I get close to the 5, it dominates because of that 1 over r squared. When I get close to the 4, it dominates because of that 1 over r squared. Now, indeed, I can take a point and just drag it around. Ooh, very large. Okay. Now, one representation would just be to click everywhere and just have just a bazillion of these arrows. That's not helpful. So, instead, I'm going to use directional arrows. Now, these are arrows that point in the direction of the electric field, but they're always the same length. Okay? And he's used a color coding to indicate the strength of the field, but we're going to ignore that. And with those directional arrows, I can do something interesting. If I come over here to the 5 and click, that's the direction of the electric field, radially outward. And if I march to the end of that arrow and click again, and keep doing that, I get a line that's called a line of force. Now, you're going to learn about that in next week's tutorial. Does anyone want to guess where this is going to end up? Yeah. Now, it's called a line of force because if I go back to the electric field vector, anywhere I click near that line, the electric field is going to be tangent to that line. Well, that makes sense because that's how I made the line. I asked what direction is the electric field, and I went in that direction, and I kept stepping. Now, David's program, this is the genius here, he allows the the computer to do the same thing. If I click right here, it will create a line of force. Now, you'll notice the computer got a different answer than I did. And that's because I only took steps. I took like 12 steps, and the steps were big. The computer took 1,000,000 steps, little tiny steps, and followed it along the way. So the computer's line is more accurate. Now, if I take those lines and I create a set of them, let's say I use 5 lines to represent the 5 coulombs, I should have how many lines for the -4? 4, and I'm missing one. So I go in and I put that line there. Now, that's kind of a sloppy representation. I can get a better representation by using 10 lines. Now, if I've got 10 lines for the 5, I should have 8 for the -4. I've got 1, 2, 3, 4, 5, 6, 7. I'm missing one right there. Now, what I was trying to do, I may not have been perfect at it because I'm very imperfect, but I was trying to get this spacing here the same. And clearly I didn't do a good job. But I mean, Joey, okay? Now, the reason I wanted this spacing to be the same is because close to this point charge, very close, it dominates. And if I've got a point source, the field should be radially symmetric, meaning I should get the same strength here as I do there if I'm the same distance away. Now, if I do that, if I make these symmetric around the sources, if I do a good job of that, then my field lines tell me not only the direction of the electric field, but the relative magnitude. If I go back to the vectors, where the field lines are close together, I get a big vector. Where the field lines are far apart, I get a smaller vector. Where they're really far apart, I get a teeny vector. But those vectors are always tangent to the field lines. Okay? And so these field lines paint a picture. I know it's stinky here. It's not stinky there. And I know the direction of the field. Now, questions about those field lines. On your exam, you will have a field line problem. It will be the easiest problem on the exam if you do it correctly. Okay? I'll show you in a minute. This is a summary here. The direction of the E field vector, that's this thing here. The direction is always tangent to the field line. The magnitude of the E field vector at any point is dependent on how close the lines are together, the density of field lines. When they're scrunched up together, that's stinky. That's a big field. When they're spread out, a weak field. The number of field lines leaving positive charge or entering negative charge is proportional to the size of the charge. If one charge is twice the magnitude of the other, it should have twice as many field lines connected to it. And these field lines leave positive charge and they die on negative charge. They're born on positive charge, they die on negative charge.